All right, AP students, welcome to more AP titration questions. Today we're actually going to go through two free responses, one complete short FRQ and one portion of a long FRQ. And our first FRQ that we're going to go through, question number 8 on page 18 in your Unit 8 workbook, is actually a question that really focuses on bringing in Unit 3 material, Beer spectrometry, absorbance, and concentration relationship with the concept of acid-base titration. So this is a great reminder that FRQ questions are cumulative. They very rarely focus on one unit, let alone one subtopic at a time. So you really have to be able to make the connections between previous content and how it's applied, especially in term 2 content, the second half of AP curriculum. So what we're told here is that a student is given a solution of phenyl red of unknown concentration. So phenyl red, of course, is an indicator. Solutions of phenyl red are bright pink under basic conditions. So that is going to be something that we need to remember is the more pink it is, the more basic it is for this problem. So a student uses a pH probe, which is a very accurate digital probe, and determines that the pH of the solution is 11.20. So we know that is a basic solution. Calculate the hydrogen ion concentration in the solution of phenyl red. So you know that the concentration of H plus or H3O plus, they're pretty much equivalent, is equal to 10 raised to the negative pH. Well, you were given the pH, so you would immediately just plug in. Okay, and you would get a value of 6.3 times 10 to the negative 12 molarity. And that right there is a point. Okay, so in case you were wondering, like, wait, why didn't I use POH? It's because when you see the basic value in pH, you don't have to automatically switch to POH unless they specifically tell you this is the OH, right, concentration, or the POH. But notice this was all in terms of pH, so I could easily determine my H plus value because it was given to me in the perspective of pH in the first place. I know that the interplay between when to switch between the base perspective and the acid perspective is a little confusing. It'll just come with practice. But for the most part, if the prompt gives you everything in one perspective, start with that perspective. See what you can get out of it coming from just the base perspective or just the acid perspective before you start going between them. So then we are told that the student analyzes a sample of the solution using a spectrophotometer. Well, we know, by the way, Beer's law, spectrophotometry creates a relationship between concentration and absorbance, right? So the higher the absorbance, the higher the concentration is what we've learned of the sample, according to Beer's law. This is totally a Beer's law, where A equals molar absorptivity value times the length of the pass cell times concentration. Okay, so that's kind of just like a quick review of Beer-Lambert's law and spectrophotometry. Is set at a wavelength of 559. So we know that this must be lambda max, the maximum wavelength of highest absorption. This is the wavelength where we see 100% absorbance and 0 transmittance. Okay. So this would be 100% absorbance and 0% transmittance at this lambda max. Okay. And the wavelength of maximum absorbance for phenyl red, the measured absorbance of the phenyl red solution at 559 is 0.35. So we're told that A at 539 is 0.35. Okay. So based on the calibration curve that we develop, because usually what the goal is as Beer's lemon law, we want to create a linear trend so that if we were to put in any unknown sample with an unknown concentration, we could plot it according to the trend line. Between the relationship between absorbance and concentration. What is the concentration of solution in micromoles? Ooh, micro is 10 to the negative. By the way, I believe it is to the negative, oh no, 6. I think that's correct. 10 to the negative 6. Let me just double check that. Micro. Micro unit, I believe, is 10 to the negative 6. And I'm really going to be embarrassed if it's not. So, it is definitely, yeah, 10 to the negative 6 SI units. Okay, that was almost embarrassing, especially after I told you guys to memorize those. So then we're looking at this. So what we notice is immediately, if I have absorbance of 0.35, the AP gives you data, and because it wants you to use the data. So I know at 559 maximum absorbance, okay, wavelength, which by the way, really doesn't matter at this point when you look at the diagram, because you're assuming that that maximum wavelength is set for the entirety of your spectrophotometry experiment. Okay, and then you're told you get an absorbance of 0.35. The question is, what was the concentration there? Well, at 0.35, okay, 0.35 absorbance, according to the trend that was developed between absorbance and concentration for this specific sample, I would guess that the absorbance in, or sorry, the concentration in micromolarity is around, it's between, an acceptable range would be 5.2 micromolarity and 5.6 micromolarity would be an acceptable range for the for the AP College Board to have you extrapolate from the data. Okay, so here this is all graph reading, right? Now we're asked if the student's mix is 10 milliliters of distilled water with 10 milliliters of the sample, would this diluted solution have an absorbance greater than, less than, or equal to the absorbance of the solution? Justify your answer. So what you need to keep in mind is that because concentration is, okay, the direct value, one of the direct factors that we're connecting, right? We're connecting absorbance and concentration. We're creating a direct relationship between them. Molarity does in fact matter because we measure concentration and molarity. So you know that the value of molarity does indeed matter. So when you dilute it, the answer would be, yes, it does affect the absorbance. So when the solution is diluted, okay? When the solution is diluted, the absorbance will be negatively affected. And if we know that absorbance is proportional or directly related to concentration and we dilute, we would know that if I decrease my concentration, I would also decrease my absorbance. So we would know that the absorbance will be negatively affected and the value will, the value of absorbance will be less than the original solution. Okay. And you need to consider that this aligns with Beer's law. In fact, the AP does ask you to state exactly how you know this. How did you know this relationship? Because it's in accordance with Beer's law. So when the solution is diluted, the absorbance will be negatively affected and the value of absorbance will be less than the original solution as illustrated or defined. Maybe we could say as described in Beer's law. That right there is a 2-point question, okay? I think the biggest thing that you guys forget is when you explain things, use the terminology, right? Don't just describe what's happening, even though that's definitely part of the points of as justification, like actually connect it with the scientific principle, right? Use the terminology. So if you know that you we're using Beer's law in order to describe this relationship and make this prediction, just state you use Beer's law. So let's now talk about part D. If a student measured the absorbance of a solution at a wavelength of 615 nanometers, okay, so that would be what we did is we just increased our lambda max, okay? We are changing our lambda max. Would the absorbance be greater than, less than, or equal to the absorbance of the solution at 559 nanometers? Justify your answer. So we know that at lambda max, the correct lambda max, I should emphasize, we get 100% absorbance, okay, and 0% transmittance for a sample. So anytime we change that absorbance lambda max value, we are now not getting 100% absorbance. So what would happen is that our absorbance values would definitely be less than. So if lambda max is changed to 650 nanometers, we would see absorbance values less than those taken at lambda max 559 nanometers because, and this is where you would earn 2 points, because only at lambda, because only at the correct lambda max 559 nanometers, we see 100% absorbance, okay? Any other lambda max would report lesser values. All right, so right there. All right, good job, you guys. That is the conceptual. Now I have one more I want to walk through, and this one is actually part of question 9. And it focuses on some mathematical processes, calculations that I went through in class on just general titration problems. So hopefully this question was a nice review on Beer-Lambert's law. And let's go ahead and pop on down to question 9, kind of the second portion, the second sub-prompt within question 9 on page 20. So here, we're going to take now a more mathematical view. We have a titration. They're just talking about compared to the one above. It's basically its own question. In a different titration, okay, a 0.7529 gram sample of a mixture of solid benzoic acid, that is benzoic acid, and solid salt, NaCl, is dissolved in water and titrated with 0.150 molarity NaOH. The equivalence point is reached when 24.78 milliliters of base solution is added. So first and foremost, you're actually given way more information that you need in this. Notice they tell you that you are mixing with salt. Okay, salt doesn't matter. Salt dissociates as soon as it's in water, and it definitely is not an acid or a base itself. So that doesn't matter at all. You can completely ignore that salt. So what it really comes down to is this benzoic acid, which is a weak acid, and this strong base. Okay. And so what we're asked is calculate the following: the mass in grams of benzoic acid in the solid sample. So we know at neutralization, we have to have our moles of acid stoichiometrically equal our moles of base. So the benzoic acid is going to lose 1 H, and the NaOH is going to lose 1 OH, okay, for every neutralization completion of a neutralization reaction. It's going to be a 1-to-1 ratio. So here's how I know that: NaOH plus C6H5COOH, carboxylic acid, okay, is going to go to Here, it's actually going to go to dissociated Na plus H2O and C6H5COO minus conjugate base carboxylate. So that's kind of what we get in the reaction. The Na plus is just a spectator ion. It just kind of carries the OH that really matters. And we're going to see the exchange of an OH basic ion and an H plus acidic ion. And it's going to be a 1-to-1 ratio. So what that means then is when we calculate the moles of acid, okay, are actually going to equal the moles of base when we think about stoichiometrically, because it's a 1-to-1 exchange in neutralization. So that means that all we have to do is find the moles of base used, titrant, and use that to work backwards to find the moles of acid. So that's easy for us. We know that we used, okay, we used how many liters? 24.78. So 0.02478 liters of NaOH times the molarity value. So 0.150, and I'm going to break this up into this derived units that make up the molarity, which is moles per liter. And then we get a value of 3.72 times 10 to the negative 3 moles of NaOH. And we know that if I use this many NaOH, that I also have a stoichiometric relationship that for every 1 mole of acid, I'm just going to make my life easier, I used 1 mole or required 1 mole of NaOH. So that means I also indeed use 3.72 times 10 to the negative 3 moles of acid were neutralized. And then all I need to do is to get from moles to grams of that acid, I'm going to simply use molar mass. And I'm going to quickly shrink all of this because it got a little big. Okay, there you go. I know then that I can just use the molar mass value of benzoic acid because this is how much I needed in the, this is the mole value of how much I needed or how much I did neutralize in the first place, the original amount of sample that I neutralized. And the molar mass of benzoic acid is around 122 grams. Okay, I'm just gonna make my life easy and write acid instead of the entire compound. And per 1 mole, making sure, of course, that my units cancel so I know that I set this up well and I'm left with the units of grams of acid, and I simply finish out the math and I get that I used or neutralized in the original sample of 0.453 grams of benzoic acid was in the sample and was fully neutralized based on my known standardized titrant solution, NaOH. All right. And I am watching sig figs. I am in 3 sig figs because my molarity of my NaOH was 3 sig fig. It was the value that limited me in my sig figs. So now the next question is, well, what's the mass percentage of benzoic acid in the solid sample? So when we think about mass percentage, you have to think about, okay, mass percentage is kind of similar to mass purity. Like, what was the actual amount of pure benzoic acid in the sample that I was given that was a mixture of benzoic and salt? Okay, so here now is where you actually do care about salt, because the salt here is not reacting, but it is taking up a portion of your sample mixture. It is contributing to the contamination or the impurity of your sample mixture. So you know that in part A or part C, I guess, part C1, you figured out that this is technically the pure value or the value of pure sample of pure acid reacted. This is the value or amount of pure acid neutralized. So that tells you how much actual benzoic acid was in that mixture. So you know that the percent mass is going to equal, or percent purity is going to equal actual over total times 100, right? So we're told that our actual that we determined in part CI is 0.453 grams. But according to our prompt, we were told that we started with a mixture of the sample, a mixed sample size of 0.7529 grams. So all you have to do now is complete the calculation and you will get that our mass purity or a mass percentage of benzoic acid actually present in the sample that was then neutralized completely by the NaOH was 60.2% of that mixed sample. And that is your answer. So great work, you guys. That's kind of our walkthrough. And quick reminder that for as we look toward wrapping up this calculation dense unit 8 section, that you really understand the process, right? Really understand why each step goes in this order, why you put the numbers in this specific place, when to use the numbers, where do you get the numbers, and so forth. Go back to your notes, reference the outlines along the side of practice problems where I gave you the process or the step flow chart. And then, of course, treat every problem like a learning opportunity to review and connect with old material. So good job, you guys. Best of luck.